Have you ever wondered how mission-critical systems, like spacecraft controls or life support equipment, manage to keep working flawlessly, even when individual components fail? It seems almost magical, but it is a testament to clever engineering. At the heart of this incredible reliability lies a powerful concept called N-Modular Redundancy, or NMR. Simply put, NMR is a robust fault tolerance technique that uses multiple identical components, often referred to as modules, to perform the same task simultaneously. This parallel execution significantly enhances a system's overall reliability and availability. The core mechanism behind N-modular redundancy is surprisingly elegant. Imagine you have a critical calculation that needs to be absolutely correct. Instead of trusting just one processor, NMR employs n number of processors to execute that exact same calculation independently. Each processor, or module, produces its own output. These outputs are then fed into a special component called a voter. The voter's job is to compare all the results. If one module produces a different or incorrect result, perhaps due to a transient error or even a permanent failure, the voter identifies the discrepancy. By design, the voter then selects the output that is agreed upon by the majority of the working modules. This means that a single faulty component does not bring the entire system down. It is effectively masked by the correct operation of its redundant counterparts, allowing the system to continue functioning without interruption. The number n is typically an odd number, like 3 or 5, to ensure a clear majority for the voting process. While the concept is straightforward, implementing N-modular redundancy requires careful planning. It is commonly deployed in systems where downtime is simply not an option. Think about flight control systems in airplanes, nuclear power plant safety controls, or critical medical monitoring devices. For these applications, the financial and safety costs of failure outweigh the increased complexity and expense of implementing NMR. Deciding when to use NMR involves weighing the criticality of the system against factors like hardware costs, power consumption, and the overhead introduced by the voting logic and module synchronization. One of the most widely recognized forms of N-modular redundancy is triple modular redundancy, or TMR, where n equals 3. This setup allows for one module to fail while the system still produces a correct output based on the other two. An interesting insider detail is that the reliability of the voter itself is paramount. If the voter fails, the entire NMR scheme collapses. Therefore, voters are often designed to be extremely simple and robust, or they might even incorporate their own form of redundancy to prevent a single point of failure. NMR is particularly effective for hardware failures or specific types of software errors that lead to divergent outputs, making it a cornerstone in achieving extremely high levels of system integrity. Ultimately, N-modular redundancy represents a proactive engineering strategy for building systems that can literally shrug off component failures. It moves beyond merely detecting errors to actively masking them, ensuring continuous operation, and maintaining an unwavering level of service even in the face of adversity. This capability is absolutely essential for applications where reliable, uninterrupted performance is not just a feature, but a fundamental requirement.
If this helps you code smarter, like, subscribe, and stay tuned for more.